Welcome to the second lecture of optical sensors course. So, in the first one we saw what are sensors and biosensors, what are the components involved in a sensor, what are the roles of each of the components in the sensor, and then we discussed various transduction methods, and from there we come to the point that you name a sensor based on the transduction method. So, if it is an electrical transduction method, you can call it an electrical sensor. If it is an optical transduction method, what it means is that the interaction between the analyte and the biorecognition element leads to change in the optical readout, that is an optical sensor. And then we discussed what are the parameters which need to be probed to make an optical sensor. For example, there was electric field, I wrote this equation and you saw that it can either be amplitude or intensity and then the phase part. So, that is all. Now, we are going to discuss the sensor fabrication and characterization. What are the functionalization methods and other performance parameters which need to be seen. So, criteria for functionalization protocols is that for the immobilization or functionalization of a biomolecules on a particular support, the very important thing is the selection of a suitable protocol or the substrate, and then we use immobilization or functionalization process, and that is different for different kind of applications. So, what is the meaning of this functionalization or immobilization? So, the meaning itself is hidden in the word itself. It means that you block, you restrict the mobility of a molecule on a surface, that is immobilization. That is in terms of the molecule. When you say in terms of the substrate or surface, then you put the molecule. So, basically you did a certain functionalization of this surface. So, these are the meanings of this immobilization thing, like you restricted the mobility of the molecule by attaching it to on the surface. So, there are certain criteria for this surface, that this surface or support should be homogeneous and it has to be stable, be it chemical stability, be it physical stability or biological stability. And the protocol and the support both should be non-toxic and immune to environmental conditions, say for example, pH or temperature or humidity. So, it should not be like that okay, this protocol changes with temperature or substrate or surface changes with its properties with say humidity, then this will not be a good sensor. Why? Suppose you have a sensor and it is working fine in normal weather conditions. Now, it started raining, the weather becomes humid, the properties of the sensor will change. Then you will need to characterize it again and again. So, the best way to avoid this is to choose a support and a protocol for binding of this molecule which is not affected by ambient conditions, okay? And the support should be non-reactive to immobilized molecule or the product of the final reaction. What it means? It means that you immobilize a molecule on the substrate and then it starts reacting with itself, then your sensor is not good, because this will lead to faulty signals. Okay. Also, suppose you attach this molecule, this is a BRE, you functionalized this, you attached it, immobilized it on the surface, okay, it does not react with the surface, but then comes the analyte, it interacts with the BRE, it leads to another product which starts reacting with the surface. This is also not good. So, the choice of the protocol for sensing and the substrate is very important. It should have, the substrate should have several functional groups, so that you can immobilize the molecule and the protocol shall have good capability to hold them for a long time. It is not that okay, it came, it got attached, after certain time it goes bad. So, it is basically the sometimes the support selection demands the application specific characteristics of it. So, one has to be very specific according to the application, one has to choose the support and also the transduction mechanism. For example, you cannot use a wooden surface for optics. Okay. Okay. So, let us go to the immobilization techniques. Covalent bonding, one of the immobilization techniques very favorable is covalent bonding. Why? Because covalent bonds are very good. So, if you have a support like this, you attach the molecule using covalent bonds. It can be any of these bonds, it can be an amide bond or amidation reaction or SIF base formation, EDCHS chemistry. This is very good in I told you this antibody and antigen reactions, this is very good for attaching them. Thiol disulfide interchange, thios and disulfide bonds are good for bonding on metal and diazotization. Why it is good? Because it is resistant to the changes in temperature, ionic strength, pH of structure of the ambient. It can be reused and recycled, but the problem is that it may suffer from potential loss of activity of the molecule. Why? Because it is attached firmly. After certain time, there is a possibility that the molecule will start lose, as the sensor surface becomes older and older, it will start losing its activity. That is the reason that there are certain limitations. There are various kind of covalent bonding, say thiol bonding I told you. Thiol is basically organosulfur compound which contain carbon bonded sulfur SH groups, and this makes very good bond, that is basically coordinate covalent bond, and it makes a very good coordinate covalent bond, very strong bonding with metal ions to form a metal thiolate complex. So, the lone pair of electrons which this sulfur have, it is donated to the metal to form a bond. So, people generally use 4-amino thiophenol, it has basically this kind of structure. One side you have SH, another side you have NH2. So, if you count from 1, 2, 3, 4, 5, 6. So, this is called 4-amino thiophenol. So, on the fourth one you have a metal surface here, and this NH2 is free for bonding of other molecules. Okay. Then you have disulfide bonds. Disulfides are another molecules which have two thiols, one binds to the substrate, other binds to the molecule. It is a very strong bond. Okay. Then you have metal bonding, it is really weak bond. So, ligands can bind sometime directly. So, this is very good for specific amino acids, and it is easily regeneration of support matrix. So, basically you do not need to, because it is loosely attached, if you want to regenerate the surface for sensing it again and again, you can easily do it. Sometimes analyte can go directly bind on here very easily, but the problem is that this will lead to something called non-specific binding, non-specific binding. So, when you have non-specific binding, then it will lead to false signals, faulty signals. So, one has to be very careful. I mean, this metal binding is not very appreciable for making real sensors, because it does not have very good response. Why? Because it is loosely bound. So, the regeneration, I mean repeatability is a problem. Repeatability, I will come to that, these things, what is repeatability and all these things. So, repeatability is a problem. it will not have a repeatable signal. Sometimes there are 5 and then sometimes there are 4 molecules, one washed away because it is very loose bond, weak bond. So, it is not very good. Then there is selenization. This is the process of covalent bonding of various kinds of silanes. These are kind of molecules which attached, actually they have siloxyl groups here, which leads to attachment on some surfaces like silica. Silica, silica like glass, it is something very difficult to attach anything on. But what happens actually that if you treat the glass with piranha solution, actually it should be like H2SO4 and H2O2. What happens actually that it gets hydroxylated OH groups, and on these OH groups these silanes go and bind on. So, then you have this works as a cross linker. In the first lecture I told you that sometimes you need a molecule as an adhesive which attaches basically the biorecognition element to the surface. So, for example, this kind of selenization functionalization works for this purpose. So, you have free NH2 molecules where you can bind your BRE bioreceptor. Okay. Then you have entrapment. Entrapment is also an irreversible process where volume molecule is basically immobilized in the lattice structure of a polymer membrane. What it means? It means like you have a polymer where these molecules are everywhere embedded, and this polymer has to be porous. So, if it is porous, then what will happen that the analyte will tunnel through, reach to this molecule, and there will be a change in signal. So, that is how a sensor based on entrapment works. So, it is very good activity. Why? Because the molecule is not immobilized, basically it is free almost. So, it is good, it does not lose its character when it is immobilized like this, because it is not like firmly attached, this is somewhere moving in a polymer matrix. So, you can put more and more molecules, so it has high loading capacity, but the problem is it has diffusion limitations. So, suppose the pore size is small and the analyte sometimes is bigger. So, I mean every time you have to choose certain optimum conditions. For example, you have a polymer and there is a certain pH condition, say acidic conditions, the pore size will be different, the aqueous conditions it will be different. So, the diffusion rates are different in different conditions, that can lead to faulty signal. So, this is a very good sensor, but again there are certain limitations to it. So, it can work for certain places, but certain places it does not work. Then you have encapsulation. In encapsulation you have a semi permeable membrane and all the biomolecules are in it. So, again it is a loosely bound thing. Since the membrane is semi permeable, the biomolecules cannot go out, but the analyte can come in. Since this is freely floating inside, so the reactivity is not changed, that is good, and analyte molecules can come and go. So, it is like bidirectional diffusion. So, probability of contamination of these biomolecules is less, because biomolecules are not going away, they are encapsulated, they are in a fixed place. At the same time there is a contamination due to perforated membrane. Why? Because now the analyte is coming and getting immobilized in the inside the membrane with the molecules. The bacteria can also come, other things also come and get bind there. So, since there is a free flow, you are never in control of passage of fouling agents. say for example, if you have a molecule this big, okay, if it can go through, then smaller falling particles can also go through. So there is a certain limitation to this kind of sensor, but it's still okay. Then there is cross linking. This is also an irreversible process. All of them are irreversible process. I will tell you what is a reversible and irreversible process. The good thing is that you don't need any support mechanism, like you needed a polymer matrix for embedding, entrapment, encapsulation. We need a semi permeable membrane, but here we don't need any support mechanism. It's free. All the biomolecules bind to themselves. It's called cross linking. So this is a very stable method, but if you use harsh chemicals, then it is less applicable. It's not so easy, okay. And the molecules which do a cross linking has to be very pure, highly pure. So to make a highly pure biomolecule, I mean improve the purity, it takes lots of money, lots of time and lots of labor. Then there is adsorption. Adsorption is a reversible process. Molecule can come, go attached on it and it can go again, like this. It is not like this pen, it got fixed here, it is not moving easily, right, it is not moving, but adsorption is not something like that. Molecule can come, get adsorbed, again there is a high chance that it will again leave and again come and again. So, it is a reversible process, because this is based on very weak interactions. It can be a van der Waals force, it can be a ionic interaction or affinity bonding. So, because of this it is a very simple process, it is low cost, retentive and fast technique. But due to weak interactions, again I told you in the beginning when I was talking about metal bonding, because due to weak interactions the rate of leakage of biomolecules is high. So, the loading capacity like attachment is random and binding is unstable. So, the repeatability of the sensor is very poor. Sometimes you will have 100 molecules, sometimes you will have only 50 maybe. The sensor response is not so repeatable. Also this is very prone to non-specific bindings, because it is adsorption, anything can come and bind. So, it leads to fouling. So, there is another problem with it. Then comes molecular imprinting. Molecular imprinting is a technique for the creation of binding sites with the memory of size and shape and functional group of the imprinted molecule. I am talking about something different. For all the methods which we have talked, you have certain x, we had certain x which went and bound to certain y which was on the surface. This is not the case for molecular imprinting. All the bindings which I have talked about yet, they were all based on functional group, they have no memory of size or shape. So, any molecule having similar kind of functional group could come and bind on here. Okay. But this technique creates binding sites which don't only have the memory of size, memory of the functional group, but also the shape and size of the molecule. It is like this. Suppose someone is asked to teach general relativity or special relativity, let us say. Any teacher of physics can go and teach, does not matter what is the height, what is the shape, he can be a lean guy or thick guy or maybe taller one or smaller one, shorter one, does not matter. That person can go and teach special theory of relativity. But now, so from there you can say that okay, this guy must have some physics degree, that is why he is able to teach it. Now we come to a point, okay, I do not want just this physics guy, but also want the shape and size. Let us name it, say I want only Albert Einstein to come and teach special relativity. So, what you do is that he knows physics, but you again do something which takes care of the shape and size of this person, then Feynman cannot go and fit in there. Okay. So, that is why what something molecular imprinting is doing. Any molecule which has the same functional group can go and attach in other kind of bondings, other kind of functionalization methods, but here they cannot, because the shape and size is also defined. So, how they are made? They are done by synthesizing copolymerization of monomer carrying certain functional group and cross linker with template molecule. What is the meaning of this? Suppose you want to detect some molecule, then you choose a polymer and a cross linker which attaches to this molecule at certain sites, and they are all polymerized together. Once they are all polymerized, the molecules, template molecules, which template molecule is the molecule which we want to sense, are removed. So, this leads to a recognition site, binding site, where this molecule can go and fit in again, because now there are 2-3 functional groups and the memory of shape and size. So, it can go and fit in only in that orientation and functional group. The polymerization process depends on temperature, polymerization medium, monomer, cross linker, all these things. Okay. So, there are two kinds of imprintings, one is covalent imprinting, another one is non-covalent imprinting. In covalent imprinting, what you do is that you take the template molecule and the cross linkers together, and then first they are allowed to react, they make, and then they are copolymerized with the polymer. So, you have these guys who are working together and then they get polymerized, and then you need a chemical reaction, cleavage reaction, to take this out. While in non-covalent imprinting, everything is polymerized together, all of it is polymerized together, and then you have a solvent which can take it off, because it is non-covalent bonding. So, these are two kinds of things. So, that is good thing. What is bad about it is that, what is bad about non-covalent imprinting or covalent imprinting or molecular imprinting is that it again uses polymers, and a polymer can swell or shrink in different ambient conditions. You change the pH, it can swell or shrink, thereby changing the shape and size of the binding site. Maybe not, but maybe yes, and that will possibly lead to faulty signal. Also, the shrinkage or swelling of this polymer will lead to change in the refractive index. So, if you are making an optical sensor which is measuring the change in refractive index of the polymer due to the ambient conditions. So, it is not like that. I mean, one has to take the calibration of this thing if you are making this kind of sensor. Now, let us see what are the performance parameter of a sensor. I mean, when you made a sensor, how do you know that if it is good or not? So, there should be certain things, certain parameters which will tell what are the qualities of this sensor, if it is good or not. Sensitivity. The first thing that comes to your mind if you talk about a sensor is the sensitivity. So, sometimes in many talks people ask me, what is the sensitivity of this sensor? Suppose I am making a sensor and then I am describing this thing, and someone asks me what is the sensitivity of the sensor, and then I tell them, can you please repeat your question? Then what it says, how sensitive your sensor is. Now, I want to tell you that is a very minor difference between these two things, terminologies, a very fine line between the question what is the sensitivity of the sensor and how sensitive your sensor is. It's two different things. I will come to that. To discuss all these things, let us consider a performance parameter. I am saying, let us say that I have a sensor which has intensity and here is wavelength. So, I have a sensor, say for concentration C1 I get this lambda 1, concentration C2 this shifts to lambda 2. If I change from C1 to C2, it goes from lambda 1 to lambda 2. Let us say this is my sensor. So, if I plot with concentration, you have concentration here and say lambda 1 and lambda 2. So, I will say lambda, maybe I call it lambda resonance at 1, lambda resonance at 2. So, this is lambda resonance and I see that it is changing like this. C1, C2, C3, you have lambda 1, lambda 2, lambda 3. Okay. Sensitivity is the value of the response per analyte concentration. That means that you have delta lambda by delta C, that is the sensitivity. The slope of this curve at particular concentration gives the sensitivity at that particular concentration. Detection accuracy, how accurate is the measurement. Limit of detection, what is the minimum concentration or amount of the analyte which can be sensed. This, for which small c value, what is the smallest c possible smallest c value, that for that you have a confident value of the parameter, say lambda here, that is the limit of detection. So, if someone asks you what is the sensitivity, that means this is the slope, but if someone asks you how sensitive your sensor is, that means what is the minimum value that it can sense, that is the limit of detection. So, these are two different questions. Selectivity or specificity, this is not a quantitative measurement, it is a qualitative measurement. So, this sensor, your sensor, if you do a sensing experiment, it should be very selective to the molecule you want to sense. It should not even sense its neighbor. So, suppose you have say hemoglobin 1 and hemoglobin 2, that is say HbA1c. If you want to detect Hb2, it does not show the presence of Hb1, it does not show any response, then it is called the selectivity or specificity of the sensor. So, it is not a quantitative value, it is a qualitative response. Response time necessary for having about 95% means like you have full sensor response. You want to have a sensor response, what is the time that you will have a confident signal from it, that is the response time. Resolution, capability of the sensor to monitor the smallest difference in the analyte parameter. So, suppose you want to measure two concentrations here, small, what is the difference between these, how small is the difference C1 and C2, that means how small you can measure the lambda 1 and lambda 2, and this is not actually the property of the sensor system, or but actually it is the characteristic of the detector. If your detector has high resolution, it can resolve lambda 1 and lambda 2 very precisely, you can have good resolution. Repeatability, how many times a sensor can give a similar result in similar conditions of operation, that is repeatability. Reproducibility, if you manufacture this kind of sensors, you can make this kind of sensors in the same similar conditions the response should be similar, that is reproducibility. Noise. A sensor can have noise, which is basically the random variation of the output signal. Sometimes you may not have an input, but you will have some output signal, that is noise. Dynamic range. What is the range that this sensor can work in? So, you have the minimum concentration, that is the limit of detection, to the maximum concentration which can be measured confidently. To this range, it is called the dynamic range of the sensor. The sensor works in this range only. Linearity. A good sensor is expected to have linear calibration curve. What it means? Like I told you that lambda versus C curve, lambda resonance versus C curve, and I showed you this kind of thing. Suppose you have like this, it is not linear here. So, basically you want to have the sensitivity if you report the sensitivity of a sensor and you want it to be constant, I told you that this is the slope. So, you want to have a constant sensitivity, that is the linear part of this response. That is what most other people are concerned about, because you want to have something which is constant sensitivity, then it is a good calibration curve. So, better the linearity, better the sensor. Drift. You operate a sensor for long time, and after certain times maybe the characteristic curve will change. So, it was showing like this, now it has started showing this. So, this is undesirable actually, but it happens as the sensor gets older and older, there is a drift. But you must know what is the drift, because if you want to measure it say after 6 months, you must know that how much my sensor response should have changed. So, you correct your value accordingly. Okay. Reusability. Can a sensor be used again? It is like this, you have a sensor, it got attached something here, you got a signal, and then what happens that if you wash it, can I use it again and again? So, that is also good concern, but for financial, I mean for commercialization aspects, most other companies they do not want actually for the sensor to be reusable. So, that you use it, you throw it, and then they will make more money. Also it is something important that then if you have a sensor which is not used again and again, then you will not have the problem of this drift and all these things. So, it will have a good confidence response. Then the shelf life, what happens to the performance when kept for long time. So, you can keep the sensor for long time, and then what will happen to it? I mean if it is kept on the shelf, you are not even using it, even then it is possible, because the biomolecules and the sensor surface may get degraded, you can have a poor response. So, that is the shelf life, that up to that life the performance of the sensor is not changing. Figure of merit, this is the ratio of the sensitivity of the sensor to the width of the spectral curve. One of the width of the spectral curve, say if you have a spectral curve like this, I told you that this is the intensity and this is lambda 1 over the width delta lambda FWHM. This gives the accuracy. What it means? It means that the sensor will be accurate when you have very fine peaks. So, the figure of merit means that a sensor is good when the full width half maximum is small and the sensitivity is large. So, that is how you define it. So, let us summarize the talk. Today we discussed what are the various functionalization methods for sensor fabrication and what are the performance parameters for the sensor. If you want to make a sensor, one must know what are the things which need to be kept high and low. Thank you.